can you hear me?
Yes, good morning.
Good morning, thank you. Okay, so first of all, I want to show you something more about saddle path stability, and in particular, in about, let's say, half an hour, show you how saddle path stability is generated as an outcome by dynamic optimization models. And next, I will show you a few review exercises on the second part of this course. So first of all, let me connect with my laptop. One moment, please. This is not a full treatment of dynamic optimization, of course. I just want to show a typical problem in which we obtain saddle path. We obtain a dynamical system in continuous time, basically, and a saddle path as the outcome. I would like you what is needed here for the examination, only to be able, when you see a dynamical system, to be able to understand what the steady state is, how to write down the general solution, possibly the particular solution, and if the steady state is a saddle, being able to derive the equation of the saddle path. But there is much more of this, of course. Also with qualitative analysis, there is the qualitative analysis due to the regions of the plane and the corresponding arrows of motion. I will show you in a few minutes what is the meaning of this tool, and also I will show you why saddle path stability emerges from a dynamic optimization problem. So a dynamic optimization problem in continuous time has a time horizon from 0, now, t equal to 0, to some terminal time. Possibly it is from 0 to plus infinity. I would say in many models it is from 0 to plus infinity. Especially in macroeconomics, when there is, let's say, a representative consumer maximizing, he or she maximizing the utility over an infinite time horizon, okay? Second, there is a state variable, which is usually a stock variable. The standard notation for the state variable or stock variable is x of t. And the stock variable accumulates over time, or decumulates over time, according to the choices of the decision maker about another variable, which is the control variable, or which is a flow variable. So the stock variable cannot be changed. The level of the stock variable cannot be changed by the decision maker immediately, okay? The stock variable obeys a differential equation. So basically, there is nothing new here. The derivative of the stock variable with respect to time is a function of the level of the stock variable, and in principle, the level of the flow variable at time t, which is under the choice of the decision maker, and possibly directly on t. Usually we omit dependence on time and we write x dot is equal to g of u xt. I have to record the class, so must record the class. record. Okay. So there is a time horizon, possibly from 0 to plus infinity, state variable, cannot be changed by the decision maker. It obeys a differential equation by which the derivative, the time derivative of the stock variable depends on the level of the stock variable, but also on the decision at time t, on the decision maker, ut, and possibly directly on time. We often omit dependence on time and write x dot is g of u xt. Then we have a control variable, which is maybe the new element here. We have a control variable, which is chosen by the decision maker at each point in time. For instance, let's say xt could be the amount of the wealth in the bank account of the decision maker. And ut could be the level of consumption at each point in time. Consuming reduces the level of the wealth, okay? But on the other hand, consuming increases the utility of the consumer. So there is always a trade-off between the effect of the control variable on the objective and the negative effect that the control variable has on the stock variable, okay? If the problem is maximizing something. ut, the control variable, is usually a flow variable. What is a typical statement? You don't have to be able to solve these problems. Simple examples are in the next slides, but I want to arrive immediately at the case where t is equal to plus infinity, and this has a very simple structure, okay? ut is chosen optimally at each time t so as to maximize this quantity, which is called objective functional. It is basically the sum of the rewards over a given time horizon, okay? These rewards can be utility, can be profit, okay? So, and these utilities, let's say, or profits, depend on the level of the control variable at each point in time, on the level of the stock variable at each point in time, and possibly directly on time. Of course, these are all variables of functions of t, and this is why we have dt. Possibly t is equal to plus infinity. But this problem must be solved under a constraint, and the constraint is a dynamic constraint, and it is simply the law of motion, the law of evolution of the stock variable, okay? So I must be aware that if I select at time t a given level of u and of x, then for the next short time period, the law of motion will be like this, okay? Will depend on my choices today. So this is a constraint. This is a constraint. And the final, so we have an objective functional, something that we could say a dynamic constraint that holds at each point in time, expressed in the form of a differential equation. And the other thing is that we have boundary conditions. Typically, the boundary conditions are two. One is the initial condition, because when we have to solve this type of problem, we start from time zero, and at time zero, the level of the stock variable is given, okay? So we have level of the stock variable at time zero initially is given. Then we may want to end up with x at the terminal time, stock variable at the terminal time, any, free. We don't worry about the value of the stock variable at the terminal time. Or given. When it is free, we have free endpoint problems, and when it is given, we have fixed endpoint problems. So, now, let me just show you how the problem is transformed in general, and then in the specific case we are going to study. It is, I will focus only on point one here. We introduce a new variable. Remember, constrained optimization in a static setting implies introducing a new variable, which is an auxiliary variable, okay? It's called Lagrange multiplier. Here we do something similar. we introduce a so-called co-state variable. Now the variable depends on time, okay? So there is a value for this variable for each point in time. It's a path. It's a path over time, okay? Lambda of t. We define a function which is called the Hamiltonian, which is very, I mean, it is similar in a way to the Lagrange function. And the Hamiltonian is the integrand that you find here, f of u xt, so the integrand here, plus lambda times the right-hand side of the right-hand side of the constraint. Okay. But remember here, this is a short notation. Both u, x, lambda, and the Hamiltonian are all functions of time. Okay, so they are instantaneous functions. And next we have a kind of first order condition for a maximum. So basically, given the Hamiltonian, remember, when you have the Lagrangian, you compute the partial derivatives of the Lagrangian. Okay? Compute the partial derivatives, set them equal to 0, and this is a necessary condition for a maximum. Then it can become a sufficient condition if certain concavity conditions are satisfied. And here it is the same. We will have a set of conditions that are the so-called necessary condition for a maximum. Okay? Necessary condition for a maximum. Now, what I want to show you is that the problem I will focus on is one in which the integral goes from 0 to plus infinity, first of all. The second one is that the integrand has a simple structure. It is a function of u and x, and the dependence on t is just because this function of u and x is multiplied by a discount factor, which is a function that depends only on t, okay? So we have f of u of x, it will be something like function of u of x times exponential of minus rate times t, okay? And another thing is that since now it goes from 0 to plus infinity, there is no terminal time, it's plus infinity, so we cannot state that the value of the state variable at the terminal time is given, because we don't have any terminal time, it is plus infinity. But an equivalent condition over an infinite horizon will be stated later, okay? There are different types of conditions, and some of them are equivalent. So basically, we require that the state variable, let me say it in a very intuitive terms, the state variable and the control variable do not explode, okay? Otherwise, the solution cannot be optimal. Even if it satisfies the other necessary conditions, if it explodes in the long run, it cannot be optimal, okay? So in order to have a unique solution, which is bounded in the long run, we must impose a certain condition that you will see in the next slide. So I skip this point because next we have to show how the conditions look like in the infinite horizon problems. So this is an infinite horizon problem in which the function is of the type f of xu times exponential of minus rho t. Rho is called subjective discount rate. It is not necessarily the market interest rate. It is a rate of time preference of the decision maker. Okay? What is my trade-off between present satisfaction and future satisfaction? The rate expresses this trade-off. Of course, the larger the rate, the higher is the preference for today's utility. Okay? So this is a subjective discount rate. And of course, now we have this statement, x dot is equal to g of x mu. Another point is that we want an autonomous differential equation for the evolution of the state variable. X0 is equal to x0, but the only difference is that here we have plus infinity, and we have a terminal condition which will be according to the type and the time horizon of the problem. Here we would have a standard terminal condition, but if the problem is from 0 to plus infinity, a terminal boundary condition for an optimal path is this one. Okay? And it can be shown that in a large number of cases, this is equivalent to requiring that the path converges to a steady state, and the steady state is a saddle. Okay? So basically, if you look at this condition, the product between the state variable and the co-state variable, discounted, must converge to 0. This basically means that the state variable and also the control variable cannot grow or grow negatively unboundedly. Okay? This is against optimality. A path having these properties cannot be optimal, even if it satisfies the other necessary conditions. It can be shown that for practical purposes, in a large number of cases, this condition is equivalent to requiring that there is a steady state. The steady state is a saddle, and the optimal path converges to the steady state, which means evolves along the saddle path, because otherwise it cannot converge to the saddle steady state. Okay, so this is the reason why, of course, the mathematical methods needed to prove this are not trivial at all, not at all trivial. Okay, so it's, I mean, there is a theory of dynamic optimization in continuous time showing that the relations between saddle path stability properties and optimality. So it's a lot of it's a hard work, if you like. You can look at the textbooks for this. There is maybe something also in the textbooks that we adopted. I guess there is something about this in the two, not in the main textbook, but in the other two. Listed in the web page, there is something about this, but okay, it's just at the intuitive level. Okay, so basically, it's not. I mean, what do we see? I guess in some models of macroeconomics is simple problems of dynamic optimization, in which immediately the textbook writes, okay, the necessary conditions on the Hamiltonian are the following. And then you have a dynamic system, and next a graph with the arrows. Okay, so I just want to show you what is the meaning of this. Okay, so the reason is that a problem like this results necessarily, if it is a well-posed problem, typical problem, results in saddle path stability. Here is an example of a typical problem. I try to, and next we will study the dynamic system as an exercise. Okay, a typical problem is maximizing from 0 to plus infinity this function of both the state variable and the control variable, x minus x squared. You see, this is kind of part that depends on x, minus u squared, minus the squared of the control variable, exponential of minus rho t dt. If you look at the part that depends on x, is like this. Okay, it's a branch of a parabola. Of course, it is valid only in the part where it is increasing. The part that depends on u is like this, but it is taken with the minus sign. And the evolution of the state variable is x dot is equal to u minus delta x. This is a very simple example of the two forces that operate one against the other. Look at the state variable first. We have a stock variable, which is something that we like. Okay, so we like that the stock variable increases. Could be capital stock. In order to let the stock variable increase, we make an effort. Could be investment, and the effort is u. The larger the effort is, the larger is the derivative, so the rate of growth of our stock variable. Okay, but on the contrary, the stock variable depreciates over time, minus depreciation rate times the level of the stock variable. Okay, so in the absence of u, in the absence of effort to increase the level of the stock variable, we have something that declines exponentially. X dot is equal to minus delta x. Okay, but we make an effort. However, we like the stock variable, and this is embedded in the fact that our objective function depends positively on the state variable. You see here f of x, this part is like this. It depends positively on the state variable, but with decreasing rate. It increases with decreasing rates. It is concave. On the other hand, if we make an effort to increase the state variable, we pay a cost, and this cost is in the objective function. The larger the effort, the larger the cost. And by the way, with increasing rates, okay? So this is a typical problem, because with these assumptions, the objective here is concave function, okay? It is a concave function of both x and u, and because it is convex in u, but it is, here we have a minus sign, okay? So this is a typical setting in which concave objective function, a linear equation for the constraint, is a typical problem that can be solved very easily and results in a simple dynamical system. And it is very typical, okay? Flow variable is a control variable. We use this to increase the stock variable. The objective functional is happy if our stock variable increases, but on the other hand, we pay a cost. We have to pay a cost, otherwise the stock variable decreases, but the cost goes also in the objective functional, which is decreasing in our cost, okay? So, of course, we will have a trade-off. How is it solved? It is solved in this way. We build a current value Hamiltonian. This is something different from the standard Hamiltonian. We don't, if you remember, in the standard Hamiltonian, we put all of this quantity. Now we neglect the discount factor. This is called current value Hamiltonian. We just put this quantity, x minus x squared minus u squared, here, plus the multiplier, which is the costate variable, okay, mu, lambda, mu, whatever, times u minus delta x, the right-hand side of the constraint. Next, we apply simple conditions that are called the Pontryagin maximum principle. They are the necessary conditions for a maximum to this problem. Okay? The first condition is that the Hamiltonian, remember that this is something that depends on t, the Hamiltonian at each point in time is maximized with respect to our control variable. This is not difficult to understand. We want that the Hamiltonian at each point in time is stationary, is maximized with respect to our control variable. So we have to compute, basically, if the necessary concavity conditions are satisfied, this just results in computing the derivative of the Hamiltonian with respect to u and setting the derivative equal to 0. But the derivative of the Hamiltonian with respect to u, here x is not u, so it disappears, it's minus 2u plus mu. This is just our derivative of the Hamiltonian with respect to u. From this equation, we obtain an important relation between the control variable and the costate variable. We obtain that at each point in time, our control variable must be half the level of the costate variable. Okay? So this is the first insight. Or the costate variable is twice the control variable. The second condition is a little more complicated, but here is the formula, basically. So the second condition is like this. You can see it here. Sorry. You can see it here. It is stated here because in the first slide there is a problem in which I have a finite time horizon, but for the rest it is exactly the same. Okay. So you can look at the condition here. So the first is that the Hamiltonian is maximized with respect to u. The second is that the derivative of the costate variable is equal to rho, the time preference rate, times mu, minus the derivative of the Hamiltonian with respect to x. The third condition is just the law of motion for the state variable. This is already part of the problem. The fourth condition is just the initial condition. And the fifth condition will be that the optimal path converges to a sudden steady state. So we have all of these conditions. Okay? Let me write down for our problem the second condition, which is the only missing part. The second condition is, remember, rho nu dot is equal to rho mu, this is standard, minus the derivative of h with respect to x. The derivative of h with respect to x is 1 minus 2x minus mu delta. Okay? So minus this quantity. Now we can rearrange it because there is something that depends on mu. So rho plus delta mu minus 1 minus 2x. Now, I must say this, some textbooks now start to study a dynamical system because we have the equation on x, which is given by the problem. Okay, so x dot is equal to minus delta x plus u. And we have an equation for mu, which is the co-state variable. Mu is equal to, mu dot is equal to rho plus delta mu minus 1 plus 2x. So we have a system in x and mu. And many textbooks start to study the dynamical system. Okay? What other textbooks do, and what I prefer, is for the economic intuition to transform, if possible, the dynamic equation in the co-state variable into a dynamic equation for the control variable. Okay, so the meaning of the co-state variable is not so intuitive as the meaning of the control variable. Okay, but this is easy in this case because u is mu over 2. So mu is equal to 2u, mu dot is equal to 2u dot. So we replace to mu dot 2u dot into mu 2u, and we have transformed the dynamic equation of the co-state variable into one in the control variable, which is like this. This is the equation in the co-state variable, and this is the corresponding equation in the control variable. Then we can divide by 2, and we get u dot is equal to rho plus delta u minus plus x minus 1/2. So the fourth condition is that the initial condition is given, and then x and u converge to a set of equilibrium. Okay, so this is basically the way a problem of dynamic optimization with this structure over an infinite time horizon can result in a dynamical system of two autonomous differential equations of first order. This is a dynamical system, x dot, u dot, the two variables. If you look at the coefficients, you see that we have this matrix, minus delta, 1, 1, rho plus delta, times x, u, plus 0, minus 1/2, which are the constant terms. We have a steady state. We do have a steady state here, which is basically can be obtained by setting x dot and u dot equal to 0. So we obtain u is equal to delta x. So look here, the steady state value of the control variable is just to keep the state variable at a constant level, okay? Just enough to replace the depreciation of the state variable, okay? So the equilibrium value of the control variable is what is enough to keep the state variable at a constant level, so to offset the depreciation of the state variable. And the other results in this equation, okay? X plus rho plus delta u is equal to 1/2. If you can solve it, next I will show you a numerical example, but you can solve it and we obtain u star, x star. There is a criterion to understand immediately whether the steady state is a saddle, and it is that the determinant is negative. The determinant of what? The determinant of the matrix of the coefficients, this one. So the determinant in this case it is minus delta times rho plus delta minus 1. It is for sure a negative quantity. Why is that? Because there are a lot of properties of matrices determinants. In particular, it can be shown that the determinant is the product of the eigenvalues. Determinant of a square matrix is the product of its eigenvalues. Okay, so if the determinant is negative, this means that one of the eigenvalues is positive and the other negative. But this means that the steady state is a saddle. Okay, a numerical example. So if you set both rho and delta to 1/2, just to have a simple numerical example here, you have this dynamical system. Now we can use it as an exercise, okay, on a dynamical system. And next, I will go back to the economic interpretation of the problem at the end, when I will interpret the saddle path stability. Okay, so it is, this is the dynamical system. We can find the steady state by setting x dot u dot equal to 0. So here we obtain that u is equal to 1/2 x. Then we replace here. We can obtain x, which is 1/3, and u, which is 1/6. The characteristic equation is lambda squared minus trace times lambda. The trace is minus 1/2 plus 1, so it is plus 1/2. But here I have minus trace, so minus 1/2 lambda. And then I have minus 3/2, which is the determinant, okay, minus 1/2 minus 1. We have two eigenvalues, minus 1, 3/2. One is negative, one is positive. We can find the eigenvectors associated to lambda 1 equal to minus 1. Okay, so we build the matrix lambda 1 identity minus A. We multiply it by a vector. Here the vector is denoted V, but we could denote it as X as well. So it is basically, the two equations, of course, are equivalent to one another. We can just use one. Minus V1 minus 2V2 is equal to 0, so V2 is equal to minus 1/2 V1. So V, the first eigenvector, corresponding to the first eigenvalue, is alpha times 2 minus 1. That should be clear. The notation should be clear, right? Because it's, you know, there are infinitely many, but they belong to the same line in the plane. So we can write them in this way, which means the second component must be minus the negative of half the first component. Okay. Do the same with the other eigenvalue, 3/2. Build the matrix lambda 2 identity minus A, which is this one. Compute lambda 2 identity minus A times vector equal to 0. Solve for the vector. The two equations are equivalent. Take one of them. V2 is equal to 2V1. Second component, that is twice the first component. So this is the second eigenvector. The solution is XU. Now, of course, remember, of course, don't write the solution. Write the solution in a way that the eigenvalue matches the corresponding eigenvector. Okay, so this is the eigenvector associated to the eigenvalue minus 1. This is the eigenvector associated to the eigenvalue 3/2. This is the steady state. Clearly, this is a saddle. We can see it from the solution. But what we also see is that if, in particular, C2, if the initial condition is such that C2 is equal to 0, then we will have convergence towards this steady state. Why? Because if we can find a way for C2 to be equal to 0, only this term will belong to the transitory part of the solution, but this disappears in the long run, and the solution will be a steady state. But one could say, but however, we already have the initial condition because we have x0 is given. x0 is given, but u0 is not given. So we have to play with u0, okay? So we have to play with the control variable. We have to select a value of the control variable, which together with the given initial value of the state variable, brings our initial point exactly on the saddle path. Okay? Okay, so here is the system. This is just like this. It is written 2c1 exponential minus t plus c2 exponential 3/2t plus 1/3, and the same for the other equation. So it's written in extensive form. C2 equal to 0. If we set C2 equal to 0, we obtain that xt, so x minus 1/3, becomes equal to 2c1 exponential minus t. While u minus 1/6, move it to the left, becomes equal to, remember that C2 is 0, becomes equal to minus C1 exponential minus t, which means that u minus 1 over 6 is equal to minus 1/2 x minus 1/3. Okay? Because x minus 1/3 is 2c1 times this quantity. Here we have minus c1, so it is minus 1/2. Okay? So u is equal to minus 1/2 x plus 1/3. This is the southern part written in the plane xu. Some textbooks use the plane x in abscissa, u in a vertical coordinates. Other textbooks do the opposite. I prefer to put the state variable here and the control variable in the vertical coordinates. Okay. We can also derive the so-called unstable manifold, which is another line in the plane that corresponds to the unstable eigenvector. We do the same by putting C1 equal to 0, moving again the two constant terms to the left, and then eliminating time, getting rid of time in the equation, and expressing u as a function of x. So if we set C1 equal to 0, we get x minus 1/3 is equal to this, C2 exponential 3 over 2t, u minus 1/6 is equal to 2, C2 exponential 3 over 2t, and of course we get that u minus 1/6 is equal to 2 twice x minus 1/3. So this is the unstable path. And the next step is to represent both of them in the plane. So this line, and try to understand what happens from a dynamic viewpoint in just looking at the plane of the joint movement of the state variables and no longer at the time paths. We don't have any more dependence on time here. We are in the plane x, u. Of course, both variables depend on time, but we focus on their joint movement in the plane. So look, it's not difficult. Here I represent u is equal to minus 1/2 x plus 1/3, so-called saddle path. It is this one. The blue line is the saddle path. Okay? Plus 1/3 minus 1/2 x. Okay? It is this one. In red here, I represent the unstable path, 2x minus 1/2. It is this straight line. Of course, the two straight lines necessarily intersect in the steady state. The saddle path and the unstable path necessarily intersect in the steady state. And the reason is that when you are at the steady state, what you do is to set simultaneously C1 and C2 equal to 0, okay? So in the steady state, both this term and this term disappear, and in the stable and unstable sets, either this one or this one disappear. So if you are at the intersection, both transitory components disappear, you are at the steady state. But what are these lines, these new lines, the gray one, I guess, or the black one, and the green one? These are called the null clines or isoclines, okay? And these are important to understand the joint dynamics of the two variables. And what are these null clines? It's just the first null cline, which is called the x null cline, is the straight line that we get in the plane bisecting x dot equal to 0. This means if minus 1/2 x plus u is equal to 0, this means that the first variable, x, is at some constant level. The other variable can change, but x is at some stationary level, okay? At some constant level. It doesn't change over time. It's not constant, it's stationary. Its time derivative is 0 at that particular point. The same for u. We set u dot equal to 0 and we represent this other line. So the first is minus 1/2 plus u, which is here, So this is, sorry, minus 1/2 plus u. This is minus 1/2 x plus u. Okay, it's u is equal to 1/2 x. If you set this equal to 0, you get u equal to 1/2 x, which is here. U equal to 1/2 x. So this is the new line x dot equal to 0, the green one. What about the other one? This is u is equal to 1/2 minus x. It is this one. If you look at the two new lines, they separate the plane in 4 regions. Okay? So basically the idea is that they separate the plane in 4 regions. If you look, for instance, the green new line here, okay, along the new line, x dot is equal to 0, but above, x dot will be larger than 0, and below, x dot will be smaller than 0. So, in this region above the green line, variable x increases over time. In this region below the green line, variable x decreases over time. Okay? We can do the same for the other new line, u dot equal to 0, which is u equal to 1/2 minus x, which is this one. On the one side, they are just simple inequalities in the plane. On the one side, u dot is negative, on the other side, u dot is positive. On this side, so below and on the left of this new line, u dot decreases over time, on the right, u dot increases over time. So basically, we have divided the plane in 4 regions, each characterized by a given direction of motion of both variables. So basically, in this region, this portion, both x dot and u dot increase. If both x dot and u dot increase, in this region, the movement of the arrows must be northeast. Okay? Because they both increase. For instance, in this region, you see that x dot decreases, but u dot increases. So u dot increases, x dot decreases. So in this, the movement must be northwest. Okay? So we can do the same for any other region. And the final, of course, you don't need to be able to show that in the exam, of course. This is just to let you understand maybe some of these pictures you may find. What happens here? And another rule is that when the path crosses the x dot equal to 0 new line, its slope must be vertical, you see? However, when one path crosses the other new line, which is u dot equal to 0, this one, its slope must be horizontal, okay? So it must be a stationary point with respect to one axis or the other axis. Given this, you can see, for instance, that if you start from this point, in this part, in this portion of the plane, the movement is in this direction. When it crosses the new line, it must be vertical, but in this portion, the movement must be in this direction, okay? So it will move towards the unstable path. But what matters to me, what matters for understanding the model is that the optimal solution must be here, okay? So suppose, for instance, that the initial level of x is here, where there is my hand here. Here is x0. So basically, the prescription of the optimal solution is that the decision maker should be able to select exactly this level as u0, okay? In such a way that x0, u0 is in the saddle path. When x0, u0 is in the saddle path, then u must be changed over time in order to increase along this line. X will decrease along this line until the point converges to the steady state. So the meaning is, there is some optimal level of the stock, which is here. If you start with a higher level of the stock, you must select an initial level of the flow, control variable, which is here. So smaller than the optimal level, smaller than the steady state level, in such a way to be on the stable set. And in this way, you must gradually increase the flow. This will make the stock decrease as well, because the flow increases, but not too much. So the stock increases, the stock decreases until the stock reaches the steady state. Why does the stock decrease even if the flow increases? Because if you move from this point towards the steady state, you see that the stock increases, the flow increases, and the stock decreases. So the question is, why does the stock decrease even if the flow increases? Because there is depreciation. So you are less than offsetting depreciation, okay? And the final result is that it will converge to the stable, to the saddle equilibrium. Suppose that the initial level of X0 is here, which is much less than the optimal long run level. Okay, the initial level of the flow must be here, in such a way that you are in the stable arm. Next, the movement will be in this direction. The flow will gradually decrease, and the stock will increase, because this flow is already much higher than the depreciation level. So even if you increase the flow, decrease the flow, the stock will increase until it reaches the steady state, okay? So from this graph, you can then derive the optimal policy over time, because of course, time is not expressed here, it's not visible here, but one variable increases over time, the other variable decreases, so you can represent both. And you can have your basic. So it's amazing, this is just a comment, that the macroeconomics assumes that the decision maker is always able, using this variable u, which is called jump variable, not just by chance, it is called jump variable, it is able to jump exactly on the saddle path, which could be reasonable. So that the assumption about the model knowledge, okay, of the decision maker are very strong, okay? What I would like to say is that it's not so strange to assume that if we have a linear system, but if we have I just want to point out that if we have a non-linear system, all of this that you see here, all of these straight lines, the stable set, the unstable set, the new lines are non-linear curves in the plane, okay? So they are non-linear curves in the plane. It's possible to divide the plane as well in regions, but they are not portions of the plane divided by straight lines. They are more complicated portions of the plane, okay? Also, in other models, we have a steady state, maybe identified by non-linear curves, but we may have additional steady states that are not saddle, okay? But, of course, what is optimal is the saddle steady state, the solution converging to the saddle steady state. So in those cases, assuming that the decision maker can immediately jump on the saddle path is a very strong assumption. And another thing is that this is a deterministic model, but assume that there is a very, very small noise. And the prediction of this model is that if you are on the saddle path, but there is an exogenous shock that moves slightly above the saddle path, in principle, this would start a trajectory that diverges. So another implicit assumption is that the decision maker is always able to react optimally to all of the exogenous shocks that hit the system, because otherwise the system will be moved away from the saddle path. So this is the picture. But anyway, from the point of view of the mathematics, everything is here, and there is nothing new, okay? This is another example that results in the same map, so in the same dynamical system, but it has a very different meaning. I would like you to try to solve it alone, to derive the dynamical system alone, by yourself. And the equation formally are the same, but the meaning is completely different. Now, what is in the objective function is u minus u squared, but this is the control variable minus x squared, okay? And here we have x squared is equal to u minus delta x. What is the meaning here is that the stock, we are not happy if the stock increases, Okay, so that could be a model applied to the stock, for instance, of pollution. Okay, the stock of pollution has some natural rate of decay, but it increases depending on you, which is the level, for instance, of output. Assuming that the emissions are proportional to the level of output, for instance, we can assume that the larger is the level of output of the economy, the larger is the derivative of the stock of pollution. So this is the state equation, the equation of motion of the state variable. What is in the objective function? The objective function depends positively on the output. This is a function increasing and concave in U, but it depends negatively on the stock of pollution. Okay, so you have formally the same dynamical system, but now the state variable is expressed in something which decreases the objective function. Okay, but anyway, you find the same, basically the same solution with a completely different interpretation. So you can just try to derive, also in this case, the saddle path, and try to understand what happens. Of course, here the stock variable is the pollution, the control variable is U, which is the level of output. So you can decide, it is a flow, the level of output is a flow. You can decide at each point in time to change the level of output, and this can be regarded as the jump variable in this model. Okay? Okay, this is just to show you how basically a dynamic optimization problem with a simple structure always results in a dynamical system having a saddle state. Okay, so this is what I wanted to show about. So I mean, for the sake of the examination, only being able to solve, writing the general solution, obtaining the steady state, possibly derive a particular solution corresponding to an initial condition, and being able to derive the saddle path, if it is a saddle, okay? To conclude about stability, and if it is a saddle, derive the saddle path, nothing more. Now, I want to show you a few review exercises. This was already the review exercise on matrix operations, seen yesterday. Now, there is another set of exercises about dynamic analysis. Okay. Let me just select the exercises. Tools more. This. It was more than this, and this, where? Okay. Okay, you see. So the first review exercise is a summary exercise on stocks and flows, definite integral and differential equations. So you have a stock variable, I could call it X, suppose it is capital stock. Capital stock is K of T. We have a flow variable, could be Y or U. This is investment here, I of T. And we consider 4 alternative scenarios for the time evolution of the capital stock, all assuming that the initial level of the capital stock is 100. One is a simple scenario in which K dot T, the derivative of the capital stock, is equal to IT. And IT, the investment flow, is constant at the level 10 per unit time. This is scenario A0, okay, the basic scenario. The second scenario is one in which the capital stock evolves in a similar way. K dot T is equal to IT. with IT is something that is not constant, but decreases gradually over time. It is expressed by 10 divided by square root of 1 plus 0.5t. But in these two scenarios, initial scenarios, K dot depends only on the flow IT. Here is a more rich equation. K dot now depends both on the level of investment, assumed constant, 30, but also on the existing level of the capital stock. So it is equal to minus 1 over 5 KT plus 30. Okay. And the final scenario is K dot T depends similarly to the current level of the capital stock. So it's basically this is like having a depreciation rate of 20%, okay? Minus 1 over 5 KT plus 42 times exponential 0.01t. So we have here an investment path that increases exponentially over time. And the solution, the question is find an analytical expression for KT in each scenario. All of these are regarded as possible evolutions of our stock variable, assuming an initial level of the stock variable equal to 100, okay? They will result in 4 different paths. By the way, technically speaking, you don't need differential equations here. You don't need differential equations here. You need differential equation here and here, okay? The first two, the answers to the first 2 points is just computing integrals, but remembering that K0 must be equal to 100, okay? So basically, they can be regarded either as definite integrals, if you are able to set up the problem from the beginning as a definite integral, or just you can find an indefinite integral, but then impose this initial condition to find the value of the arbitrary constant. So this is basically what you have to do. Let me start with the basic scenario A0. Integral of IT dt. Because it's K dot is IT, so the derivative of K is this. If I want to find K, I have to compute the integral of this, okay? Integral of IT dt is the integral of 10 dt, it is constant. It is 10t plus c, because the primitive of this constant is 10t plus c. This is kt, but it is not fully specified. We have to impose that k at time 0 is equal to 100. This means that when t is equal to 0, 10 times 0, which is 0, plus c must be equal to 100. So kt is 100 plus 10t. So the trivial part of the capital stock in this case starts at 100, it increases linearly with the slope, and the slope is exactly given by the constant investment per unit time, per year, for instance, or per month. Okay, so this is the basic shape. I want to show you that I remember that I discussed this already, but I want to show you that in principle, and this is useful for other problems, in principle we can express already the solution as an integral, okay? And this is useful if, for instance, we don't want to solve this. This is a correct way to express the solution. K at time t is the initial K, K0, plus the integral between 0 and t of I of u du. Why is that? The reason why we can write this in this way relies, it is just the statement of the fundamental theorem of calculus, okay? Remember that, let me just show you this. we know that IT is just k dot t, so it is the time derivative of k, okay? So if we write that k at time t is equal to k at time 0 plus the integral from 0 to t of I u du, IU, remember, is the derivative, so this is k dot t, k dot u du, okay? This is equal to this one. We are just saying that kt minus k0 is the integral between 0 and capital T of k dot u du, which is just the fundamental theorem of calculus, okay? So what is the definite integral between 0 and t of some integrand? It is the value of a primitive at the upper limit of integration minus the value of the primitive at the lower limit of integration, okay? So writing in this way is just a fundamental theorem of calculus, nothing more. And this is useful because sometimes you want to express a stock variable as its initial level. Imagine that you move it to the right, its initial level plus the accumulated level of a flow variable from 0 to capital T, okay? And this is basically what we do here. So k0 plus the integral between 0 and t of I u du. Of course, you can check that the result is correct. 100, k0 is 100. Integral between 0 and t of 10 du, because it is constant. This is 10u from 0 to t. This is 10t minus 0. Okay, so the result is the same. Now, so you always have two ways when computing integrals. One is finding the indefinite integral and specifying the arbitrary constant. The other is modeling the definite integral just from the beginning. And this is purely mathematical way. The second one is most often used in economics because you have already the solution displayed there with an economic interpretation. Initial stock plus accumulated value of the stock from 0 to t. Okay, so it's here. Second, KT, scenario A. Scenario A, which is the second scenario, now we have IT is equal to 10 over square root of 1 plus 0.5t. This is an elementary function. I can integrate this, almost elementary integral, because it is a power function with exponent u minus 1/2 of a linear function of u. So what is, now I use the second approach directly, okay? So kt is equal to k0 plus the integral between 0 and t of 10 over square root of 1 plus 1/2 u du. What is a primitive of this one? Remember, this linear function is raised to the exponent minus 1/2. So in the solution, it will have exponent 1/2 divided by 1/2, so multiplied by 2. And then there is this 10, and then it must be divided by 0.5. So again, multiplied by 2. So it is 40. 40 times square root of 1.0.5 u. Okay, so 100, and this becomes 40 square root of 1 plus 0.5 t minus, when u is 0, it is 40. Okay, so it is 60. 100 minus 40, it is 60. Plus 40 times square root of 1 plus 0.5t. And as an exercise, you can obtain the same result with a naive method. Compute the indefinite integral first, and then impose an initial value for the variable and specify the arbitrary constant. You see that the path now is different. It starts from 100, it increases over time, but less than linearly, okay? And the reason is that the flow is not 100 forever, it's not 10 forever, it is 10 initially, but then it decreases with time. So the accumulated stock increases, but less than linearly. Here is another example, the point B, scenario B. K dot is 30 minus 1 over 5 kt. This is no longer a simple integral. This requires differential equations from the solution. So it requires that we are able to solve linear, first order, linear autonomous differential equations. Differential equations with constant coefficients. Okay? You know that you might write down immediately the particular solution because we have the solution formula, or we can just compute the steady state first. Okay, so let me just show you. Can be useful. So k dot is equal to 30 minus 1/2 k. So in principle, we can either write down immediately the particular solution corresponding to a given initial condition k0, which is 100 in our case. So basically here we can write this as k dot is equal to 1/2 k, sorry, 1 over 5k, minus 1 over 5k, plus 30. We can write down the solution in this way. K is equal to initial deviation from the steady state, so we have to compute the steady state first, set this equal to 0. We get 1/2 k is equal to 30, k is equal to 150. Okay? So initial deviation from steady state times exponential minus 1 over 5 t plus steady state. This is already the solution, okay? If you don't remember the formula, remember that these problems can be solved always with the so-called superposition principle. So first we can solve the associative homogeneous equation and then add a particular solution. The particular solution will be the steady state solution, okay? So not this. We add a particular solution. So the solution to k dot equal to minus 1 over 5k is, the general solution is k, t is equal to c exponential minus 1 over 5t. On the other hand, the particular solution, k star is equal to 150. So you write the general solution, kt is equal to the sum of these two. Now, you know that you want k0 to be equal to 150. So you have that k 150, k times 0 must be equal to k0 must be equal to 100, okay? Not 150. So basically you have here that, so you want k0 equal, just to compare with this one, equal to a given level, okay? So k at time 0, which you want to be equal to k0, is equal to c times this when t is 0 plus 150. And this implies that c is equal to k0 minus 150. Okay? And if you replace here c equal to k0 minus 150, you obtain exactly this one. Okay? So you can do just find the steady state and then apply the superposition principle, or you can just remember the solution formula. So in this case, we have this solution. Okay, now k0 is equal to 100, k star is 150, so it becomes minus 50. So it is 150 minus 50 exponential minus 1 over 5t. So now it starts from 100. It increases towards an upper limit, which is 150. Different from the previous case, in which it increases unboundedly. here it increases towards steady state level. And the final model is K dot is equal to minus 1 over 5k plus 42 exponential of, it was 0.01 t, so t over 100. This is a linear first order differential equation with a time varying forcing term. So this is not constant, this changes over time. Our b becomes b of t. Okay? We have to solve the associated homogeneous system first, which is the same as in the previous equation. It has general solution kt is equal to c times exponential minus 1 over 5t. We have to find a particular solution to this system and then compute the sum of the two solutions. We know that in the exponential case, a particular solution to C can be found within a family of functions k, p of t, is equal to an arbitrary constant times the same exponential term that you find in the equation, exponential of t over 100. So we guess a solution of this type and we find A, okay? If this is true, the derivative of k particular with respect to t is A over 100 times this. On the other hand, what appears here, 1 over 5 kt, which will be moved to the left, okay? 1 over 5 kp is just A over 5 times this. Our equation must be satisfied, and this means that k dot plus 1 over 5k must be equal to 42 exponential of this. But this is A over 100 times this exponential term. This is A over 5 times this exponential term. And this is 42 times the same exponential term. So we have this equation in A, okay? So here we have 21A over 100 is equal to 42. So A is equal to 200. And what we obtain is that the very particular solution of this family is A, 200 exponential of t over 100. What is then the general solution? The general solution is solution to the homogeneous associated system plus our particular solution. Now we impose the initial condition k0 equal to 100, C plus 200 must be equal to 100, and C must be equal to minus 100. Okay? So this is our solution. Kt is 200 exponential of 1 over 100t minus 100 exponential minus 1 over 5t. So basically, it is similar to a situation in which we have a steady state, and the role which usually is played by a steady state now it is played by this very particular solution, which is this one. And starting from any other initial condition, we have a path that in the long run approaches this solution. And the reason is that the deviation from any other solution and this solution vanishes over time just because it is multiplied by a negative exponential of minus 1 over 5t. Okay? Here, this is the solution method based on it's called the method of undetermined coefficients. Then you can also try to solve it by exercise using the integrating factor method. You can also try to solve it using the integrating factor. And of course, you have to obtain the same solution. I remember that in the case of exponential, time varying term, b, when b is exponential, like in this case, b of t is exponential. The integrating factor method is quite easy. It doesn't result in integration by parts. It's just an integration of an elementary exponential, okay? So you can use both. However, when this is linear, integration by parts is less comfortable than applying in undetermined coefficient method. So my suggestion is that you always apply the determined coefficient method, and in the exponential case, use the integrating factor as a way to check your result. Okay, now I suggest that, okay, there was here an exercise on matrix operations. Next we have some difference equations. Okay, so I suggest that we take a break now. I will open, I will give you a code, and you can connect to a website to write down your opinions about the course, okay? So you can do that. And I will leave it open until the end of this class, so you can do that now or later, okay? And in the meantime, you can take a break. Okay, so we have to do this. Okay, so this will be the website you have to connect. And I will show you in a minute a code which is useful to for this task. And for me, I have to go to this website and open open. Okay, so how many students are there? So you are 1, 2, 3, 4, 5, and at home there are 10 participants. So in principle that should be 50, right? But there are more. So how can I compute? Should I consider also altri da chat? No, Marta da Venezia is, of course, tutor. But I wonder what are these? Why is there a distinction between the?
These are people that join earlier in the morning, and maybe are not following anymore, but they are in the memory of the chat.
Oh, they are in the memory of the chat.
I'm not sure.
So basically, this means that they connected to this today.
Yeah, they connected today to this.
That's not really clear. So I would just participants are 9, 10. I will create 15. 10 plus 5. Let me create a very nice number, 70. 70. Open. Okay, now there is a code here. I'm not sure you can read it, but it is here. This is the code you have to use. I will leave this open until the end of the class, so you can just take your time and do it later, and now enjoy your breakfast. Okay. Ma non vuole vedere adesso il suo compito? Può essere utile per lei. Io poi se vuole la ricevo anche oggi.
No, se comodo effettivamente ora.
Allora, lei ha ricevuto, le ha mandato il file?
Sì.
Quindi lei sa? Allora.
Sì.
Anch'io l'ho ricevuto, perché avevo chiesto anche io. Tu dovevi
Sì, gliel'ho mandato?
Sì, cioè mi ha mandato solamente...
È a posto, vuole vedere? Il compito?
Sì.
Però io sul compito non ho segnato niente, il compito è lo stesso che avete voi. Io perché non so, non scrivo sui file PDF, no? Quindi io preparo una scheda, se vuole, se lei ha qui la scheda che le ho mandato, forse ce l'ho anch'io, le illustro il significato di quello che ho scritto. Possiamo fare così, altrimenti io ci sono anche nel pomeriggio.
No, se non è più comodo ora.
Allora facciamo ora, tanto adesso ci vuole un po' di tempo per questa cosa qua, poi la potete fare anche dopo.
Professore, scusi,
Sì, mi dica.
una cosa veloce. From where we access the questionnaire from? I didn't get it.
Sorry, I couldn't get your question. Can you
Da
repeat?
dove entriamo per fare il questionario?
Aspetti, l'ho fatto vedere prima, si fa così, guardi. Abbasso un attimo. Allora, si fa così. Si va in questo sito. This is the website.
Ok.
val.unibo.it. Ok? Adesso mostro ancora il codice. Ok. Adesso però io ho voi vi ricordate quali erano le domande a cui non avete risposto? Cioè, cosa si riferivano agli errori che ho? Do you all have the code? Okay, let me write it in the chat. I write the code in the chat, so that should be enough. Okay. Ok, adesso mi disconnetto il video. Okay, so this is an example on difference equations. And also some differential equation which is somehow related to the difference equation. Okay. So for instance, xt plus 1 is equal to 2/3 xt plus b. Suppose that the initial condition is x0 equal to 70. Solve this difference equation, but preliminarily determine the value of the forcing term b such that the steady state of the model is x star equal to 120. Okay, so we know that this is just a question, the preliminary question is just a question to assess whether you know what the steady state is and how to find it. A steady state in the case of a difference equation, remember the difference, because sometimes what I see in the written examination is people setting xt plus 1 equal to 0 by analogy with the differential equation. No, this is not the case. You have to set xt plus 1 minus xt equal to 0, which means xt plus 1 equal to xt. Remember that when we have, in principle, when we have a difference equation of this type, xt plus 1 is equal to axt plus b. This is not the same, let me use this, means it's not the same model in discrete time as x dot equal to ax plus b. They are two very different models because this is a kind of change of x. So if you want a similar model to this one, or just if you want to compute a continuous time model which is similar to this one, you have to write xt plus 1 minus xt on the left. But now you have subtracted xt here. You have to subtract xt also here. Okay? So basically the equivalent continuous time model would be, so here you get a minus 1 xt, okay? So a minus 1 xt plus b. So in principle, if you replace this with the derivative, you get x dot is equal to a minus 1x plus b. So you see it is not, you must be careful with the parameters because here this parameter characterizes the value of xt plus 1 as a function of xt. Here it characterizes the value of the derivative. And the derivative is a change of x. So in principle it should be compared with x, change of x over a short time period. Now, what is the steady state for a difference equation? The steady state for a difference equation is like this, xt plus 1 equal to axt plus b. The change must be 0 from t to t plus 1. This is equivalent to setting x dot equal to 0 in continuous time models. But if the change must be 0, needs to be 0, this means xt plus 1 equal to xt. Okay? So if you, and this must be constant to some level x. So replace x is equal to ax plus b. Move this to the left, 1 minus ax is equal to b. And provided that a is different from 1, x star is equal to b over 1 minus a. This is the way we find steady states in difference equations. Now, I impose xt plus 1 must be equal to xt, and we impose that, of course, writing this is sufficient, but we impose it as constant as a consequence. So x star is equal to 2/3 x star plus b And we want this to be equal to 120. Okay. So from this, we obtain that 1/3 x star must be equal to b. So the steady state is 3 times b. Okay, 3 times b. We want 3 times b to be equal to 120, which means that parameter b here must be 40. Must be 40 in order for the steady state to be equal to 120. So the differential equation, the difference equation that we want to study is this one. Xt plus 1 is equal to 2/3 xt plus 40. The solution has a structure which is very similar to the solution to differential equations. The steady state plays a role in this solution formula, so 120. In particular, what plays a role is the deviation between the steady state and the initial level of the variable, okay? You know the solution formula xt is equal to x star, steady state plus x0 minus x star, times 2/3 to the power of t. Now, if x0 is equal to 70, x0 minus x star is equal to minus 50. Okay? So the solution is 120 minus 50, 2/3 to the power of t. Sometimes a question in the exercise is not just asking whether the steady state is stable or not, but for instance, asking to compute the limit of the solution as t tends to infinity. This means asking whether the steady state is globally stable or not, and even if you can't compute the limit, it is a very easy limit here, it is a limit of a sequence, this term tends to 0, because it is an exponential function of the base of a power, and the power is one in which the base is less than 1, is positive and less than 1. As t increases, this tends to 0. So this part tends to 0, and the steady state is stable, so the limit is 120. So it's just a question asking whether the steady state is stable or not. So the answer is it is globally stable. The limit is 120. And sometimes I ask also to provide a graphical representation, qualitative graphical representation of the solution. Qualitative for me means, of course, you don't need to put the right coordinates of the points of the sequence. You can also connect the points of the sequence with line segments. You can do that. But qualitatively correct means that you have to represent at some point the steady state. It must be clear whether the initial condition is below or above the steady state. And it must be clear whether the behavior is one that converges to the steady state or moves away from the steady state. Okay? So this means qualitative representation of the solution. Also here, if you don't remember the solution formula, remember that also for difference equations, we have this principle that governs the solution to non-autonomous, the solution to non-homogeneous difference equations. For instance, this one, xt plus 1 is equal to 2/3 xt plus 40. If you don't remember the solution formula, you can do like this. This is called the associated homogeneous equation. as general solution xt is equal to a constant, an arbitrary constant, like for differential equations, times 2/3 to the power of t. Okay? Now, find a particular solution. Add the steady state, which is a particular solution in this case. So the general solution to the full equation, which is this one, is the general solution to the homogeneous equation plus the steady state, okay? The general solution to this is xt is equal to c times 2/3 to the power of t plus the steady state. The steady state was 120, right? Now, like for differential equations, we impose an initial condition, x0 equal to 70. So what the x0 is a subscript, x0 equal to 70, imposes t equal to 0 here, 2/3 c times 2/3 to the power of 0, c times 1 plus 120 must be equal to 70, means c must be equal to minus 50. So basically, our general solution is 150, and our particular solution is 120 minus 50, because c is minus 50, times 2/3 to the power of t. So also this principle of separating, of building the solution as the sum of the solution of the associated homogeneous equation and a particular solution to the full equation is general. It holds for differential equations, for difference equations, systems, differentials and difference equations, autonomous, non-autonomous, any. It holds for any linear model, okay? In discrete time or continuous time. It's very powerful, and in some cases it helps to find a solution. So you can also use it for difference equations. Now, by exercise, compute x1, x2, x3, both using the recursive equation, which is this one, where you put b equal to 40. So you start with x0, which is 70, then you compute x1, then you compute x2 starting from x1, and so on and so forth. And using the solution formula, which is this one. Of course, these are two different types of computation that must match, okay? They must provide the same result. Okay, so remark below are two alternative ways to state the previous difference equation. Okay, in case of difference equations, the same difference equations can be stated in different ways. We might focus on the next value as a function of the previous value. What we might also focus, we might also focus on the change of the variable. For instance, our equation, this one, can be equivalently stated in this way. Xt plus 1 minus xt is equal to minus 1/3 xt plus 40. Why? Because if I subtract xt from the left side, I must do the same from the right side, okay? So this becomes 2/3 xt minus xt, so minus 1/3 xt. Okay? Also, it can also be stated in terms of mean reversion to the steady state, okay? Which is the model that we call the growth towards an upper limit for differential equation. There is an equivalent one also for difference equations, okay? Growth towards an upper limit. Xt plus 1 is equal to xt plus 1/3 that multiplies 120 minus xt. So if you write this in this way, here you put the coefficient with the sign, with a negative sign, so the sign must be plus here. Here you put the steady state, and the deviation between the steady state and x, okay? So xt plus 1 is equal, the next level is equal to the current level plus a fraction, 1/3 of what? Of the remaining difference between the steady state and the current level. This is expressed in mean reversion terms. This is a common representation when the steady state is stable. Remember, in continuous time, the model of growth towards an upper limit. Well, there are many simple models in both in economics and finance that are characterized by mean reversion. If they result in a difference equation, they can be written in this way. So for instance, just let me show you this. Suppose that in a speculative market, okay, the demand of some asset, since the market is speculative, the agents in the market look at the misalignments between the current price of the asset and some price that they believe is the fair price, the true price, the price that will prevail in the long run. This is called fundamental price in many areas of economics. They believe that an asset should be worth 100, okay? But currently it is 80. So it is underpriced. So they buy it because they believe that the price will increase, okay? They buy it. So what they do is that their demand, so their demand is positive in this case. Their demand is positive if, so their demand as a function of the current price is equal to some coefficient A times the price that they believe is the fair price, the fundamental price, minus the current price. So if it is underpriced, is below, this is positive, positive demand. If it is overpriced, negative demand, they set, okay? Next, the price, time t plus 1, usually depends. It is the current price, but it increases if there is a positive demand. It decreases if there is a negative demand. So basically, the price change from now to the next period is equal to basically the coefficient B times the demand. Okay? That clear? If the demand is positive, this is positive coefficient. If the demand is positive, the next price will be larger than the current price. If the demand is negative, the next price will be lower than the current price, okay? Demand pressure. So this is a simple model, but the demand depends on the current price, and the next price depends on the demand. If you write down the whole model, Pt plus 1 minus Pt is equal to B, the coefficient by which the price reacts to the demand, times A, the coefficient by which the demand depends on the current price, times P star minus Pt. Move this here, Pt plus 1 is equal to BA P star minus Bpt plus Pt. Okay? So Pt plus 1 is equal to 1 minus B Pt plus B A P star. Okay? This is a difference equation, linear. Pt plus 1 is a coefficient times Pt plus a constant. Okay? This is a linear difference equation. If you write this in this way, which is the same, this is written in terms of mean reversion. Okay? if you write this in this way, it's just written in terms of a mathematical difference equation, standard form, okay? Here you see the mean reversion. The price change depends negatively on the position of the current price with respect to the fundamental price. Of course, here there is also A, BA P star minus BA PT, okay, BA PT plus PT. So this is 1 minus BA PT, okay? I forgot the A here. Now what is, for instance, the steady state to this model? If you set PT plus 1 equal to PT, so it's clear that the fundamental, it's clear that the steady state is the fundamental price, okay? But you can obtain it from your equation, because if you set P star at the left-hand side is equal to 1 minus VA P star plus BA P star so PT plus 1 is equal to 1 minus BA P star. So let me write this star minus P. BA P star minus PT, PT plus 1 is equal to BA P star minus BA PT plus PT. So PT plus 1 is equal to 1 minus BA PT plus BA P star. Okay, then if you set, in order to compute the steady state, here you have 1 minus BA P star plus BA P star plus BA P star. So minus BA P star, so you get an identity P star is equal to P star. So you should, P star is equal to P star, it is equal to the parameter that appears here. Okay? So basically, if you express a dynamical system in terms of a mean reversion, clearly the long-run target value is the steady state of the model, and you can obtain here by imposing the steady state condition. So what is, for instance, the continuous time counterpart of this one? This P dot is equal to BA P star minus P. So if you set P dot is equal to 0, you get that P is equal to P star. Okay, so basically you can express a model both in terms of many models, both in terms of a mean reversion structure and in terms of a mathematical structure, which is the standard form for a differential or a difference equation. Okay, so this was just a digression on the way this can be represented. Now, if you want to solve a closely related differential equation, so one way to represent the previous difference equation is this one, okay? What is a closely related differential equation? Replace the difference with x dot. So a related differential equation is x dot is equal to minus 1/3 x plus 40. It is related to the previous one because it has the same steady state, which is 120. Okay, x dot equal to 0 means x equal to 120, and it has a similar solution structure. X at time t is equal to x star plus x0 minus x star exponential minus 1/3. Now remember that this exponential of minus 1/3 basically plays the role of 2/3 to the power of t here. And this exponential minus 1/3 plays the role of 2/3 to the power of t. And the final expression for the particular solution will be 120 minus 50 exponential minus 130. And the qualitative behavior is the same, okay? So one question could be, find the minimum time t, given the solution, find the minimum point in time t such that the difference between the level of our variable and its steady state is less than 5. Okay, so the difference between the variable and the steady state will always be negative in our model because the variable remains below its steady state level. So the modulus of the deviation will be basically the steady state minus the value of the variable, okay? We want it to be less than 5. So we replace here the solution, 120 minus 50 exponential minus 130. We want this expression to be less than 5. This means this disappears. This means 50 exponential minus 130 less than 5. So exponential minus 130 less than 1 over 10, minus 130 less than the logarithm, minus the logarithm of 10, which is the log of 1 minus the log of 10, divide and multiply by minus 3, and change the sign of the inequality. T larger than 3 log of 10, which is about 7 years, okay? So this is a simple. Once you have the solution, you can just, I mean, this part is somehow related to the study of the speed of convergence. So you can ask yourself whether, how much time it will take to approach the solution, the steady state solution, or to be in a certain interval around the steady state solution, okay? So this is basically. Okay, here there is an example of a definite integral with discounting. I remember that we already solved one of these numerically, so one where the parameters were specified as numerical values. You can do the same, you can follow the slides and try to do the same in two different ways. This is an integral between 0 and capital T, or between 0 and infinity, of a linear function of t times exponential of minus rho t. So my suggestion is that you solve this by parts, and if you must solve this by parts. My suggestion is that you do this in one step. So basically you could do. Here there is, this is just a review exercise of things that we already studied before. You can just have a look at it. But I would like to suggest you to try to solve it directly by parts, okay? By setting this as your f and the exponential factor as your g prime, because another way to solve it is to split the integral in two integrals. One is a exponential minus rho t, and the other one is bt times the exponential minus rho t. Okay? It might seem easier to split the integral, but what I think is that it's much easier to solve it directly by parts. Okay? And also remember that when you solve an integral by parts, you have two ways, and the integral is a definite integral. You have two ways, basically. One is to solve by parts the indefinite integral, and then to specify the constant, I mean, to evaluate the integral between 0 and capital T, or between 0 and infinity, it depends on the problem. And this is what I think is less likely to lead to mistakes. So if try to solve it the indefinite integral first, and then to compute the definite integral. However, in the textbooks, you usually find the solution displayed like this. Okay? So basically, what you see is that maybe it's not written here, but the integral by parts is already solved in the form of a definite integral, okay? But solving an integral by parts as a definite integral requires being a little bit careful with the solution steps, because if you have a very simple integral, which is the integral between 0 and capital T of t times exponential of minus t dt, okay, and this is your f, and this is your g prime, you have to compute g as minus exponential of minus t, okay? So remember that this integral is equal to f times g, so minus t exponential of minus t, and then this must be evaluated already between 0 and capital T, okay, minus t integral, so this is f times g, okay, minus the integral of g times f prime, which is t. This is f prime. This is the formula of integration by parts. So you can do directly this way. Remember that when you solve by parts, you get in the second step a finite expression, which is not integral, is already part of the solution, plus another integral, minus another integral. If you solve directly the definite integral, you can express directly both between 0 and t. But you can also just forget about this, solve the indefinite integral, find the solution, and then specify the constant. Of course, you have to obtain the same. And for this type of integrals, it is very useful to use both techniques and then to compare the results. Okay? So in this case, we would have minus t exponential of minus t, okay, which is this here, minus this evaluated at 0, which is 0, okay, minus, what is the integral of exponential minus t, sorry, no, f prime is 1, of course, because otherwise we don't solve anything, f prime is 1. Okay, here we have the minus, what is the integral of minus exponential of minus t? It is exponential of minus t, right? Right? Okay, so what we get here is equal to minus t exponential minus t minus, here is exponential of minus capital T minus 1. So basically the final result is 1 minus exponential of minus capital T minus t exponential of minus capital T. Okay? Or, okay, there is a common factor here equal to 1 minus exponential of minus capital T that multiplies 1 plus capital T, if I'm not wrong. Now, in order to check our solution, we must just compute the derivative with respect to capital T. by the fundamental theorem of calculus, this is equal to t exponential minus capital T exponential minus capital T. I am computing the derivative with respect to the upper limit of integration, okay? Now, this must be the same as what we obtain here. Let's hope that we obtain this. So the derivative with respect to capital T of 1 minus exponential minus capital T times 1 plus T is equal to, so 1 minus the derivative of the first times the second plus first minus the derivative of the second times 1. So minus exponential minus t and plus, no, sorry, this is here. So it's capital T. Okay, what remains here is minus, this is minus exponential minus capital T, minus t exponential minus capital T, okay, plus exponential minus capital T, this and this, equal to plus t exponential minus capital T, which is exactly this one, okay? So, is that clear? So this is a summary example for integration by parts, in which we display the result already as a definite integral, but the first part is already part of the solution, the other part is an integral. When we have the solution, we can check the solution by computing the derivative with respect to the upper limit of integration, if we have an integral between 0 and some terminal time, okay? And the other way you can compute the integral, and I suggest you to do that, is to forget about the integral between 0 and capital T, just compute the indefinite integral of this one. It will depend on a constant, okay? Then impose, not impose, evaluate the integral between 0 and capital T, and you will have your result, which should be the same as the one we obtained here. So it should be this one. This one. Okay? And next, as a next step, if you want to understand something more, do that. So study this one. In all the possible, with all the possible methods. This is a very useful exercise. Okay, so thank you so much, and see you online. I guess online. I guess, but I'm not sure because the rector hasn't said nothing about the exams in January so far. So I think that in principle they should be online examinations. Do you have more news, other news? Any news about that? So I think that we will know something more during the summer, the Christmas holidays, okay? I think they are still, decision is still in progress. But I think that the very, let's say, the start of the examinations only in presence will be from the summer on. I think that next month they will be online. So sorry, sorry for that.
Okay.
So bye, thank you, bye.
Excuse me, Professor.
Yeah, sure, I'm here.
Yes, before last time you gave us the list of the exercises.
Yes, I will do. Yes, sure. I will do the same also this time. I will do the same also this time.
Approximately when? I'm just curious.
Yeah, I will give you both the so-called syllabus, detailed syllabus, with the chapters and the sections in the main textbook.
Okay.
And a list of exercises.
Okay, great. Thank you. Thank you very much.
Welcome. Bye.
Yes, goodbye.
Thank you, Professor.
Goodbye. Arrivederci.
Buone vacanze.
Altrettanto, arrivederci.
Grazie.
Arrivederci, arrivederci. Buona giornata, arrivederci.